Hello, chemistry students. This is Mr. Adamski, and I have here one of my all-time favorite experiments that I'd like to show you. So what we have here is a plain beaker of water, and it is inside of a bell jar. And I'll show you the top of that so you can kind of see what's going on there. So it's kind of sealed off from the outside air. And this platform that it's on is actually a vacuum pump, and you can see that it's kind of hooked to a vacuum hose line there. And what I'm going to do is I have sealed this well enough that we can use the vacuum to pull all of the air out of that bell jar. So my question to you is, what do you think might happen if I do that? Would anything happen to the water? So let's try that and see what happens. So I'll zoom in a little bit so you can watch this a little more carefully, and let me turn on the vacuum pump. So we're going to start sucking the air out of there right now, out of that bell jar. And it's going to take just a little bit of time for that to happen because it's got to pull a lot of air out of there. And not much is happening yet. And then it starts. The water is bubbling. Have you ever seen water do that before? Bubble like that? If you said, yeah, when water boils, you would be correct. What you are watching right now is water boil at room temperature, 20 degrees Celsius, not the 100 degrees Celsius you've always been told. So let me let the air back in there, and you'll notice something else happen when I let the air back in, that everything gets really foggy there. Let's see if we can explain kind of what happened there and what's going on. So you know that molecules are constantly moving, and the more we heat them, the more they move around. So these molecules here are representing some kind of gas, and I can tell that because the molecules are not very close to one another. There's a lot of empty space between them. They're kind of bouncing around in the container. Well, normally when we have water just kind of sitting out in a beaker just out in the air, the water is evaporating. So if this was the liquid surface here at the bottom, where all those molecules would be close together, some of them can shake free and turn into a gas. Not very many of them, because they also have air pressing down on them, trying to keep them in together with their other molecule buddies there down in the liquid. This is because this pressure is so much stronger in the atmosphere, about 15 pounds per square inch, compared to the pressure that these molecules can exert with their motion, which is only about 0.4 pounds per square inch. So evaporation occurs. If I was to let that beaker sit out for a few days, I'd come back and find less water and less water. And eventually there would be none as these molecules, all of them slowly escape into the atmosphere. You get to see a little bit of this kind of thing when it's maybe a nice fall day. The water is still kind of warm from the summer, but it's cool in the air. And you can see some of those water molecules that have evaporated recondensing as tiny little droplets in the air. You're not actually seeing steam here. You're seeing water vapor droplets. This is kind of like a cloud, but it shows that there is steam there because those little water molecules can rejoin and form visible little tiny liquid droplets that are hanging in the air. Okay, well, boiling occurs when you would say 100 degrees Celsius is when boiling occurs. Yes, that is true, but the technical definition is when the vapor pressure, the pressure of the water trying to escape in this case, is equal to the atmospheric pressure. So if we heat our water up to 100 degrees Celsius, the water molecules are bouncing around more and more crazy, and eventually they have enough pressure that they are equal to the pressure of the atmosphere. And that happens under normal conditions at 100 degrees Celsius. And so that's why you've learned that water boils at 100 degrees Celsius. That's sea level. Okay, well, this is because there's so much pressure, so many of those water molecules can leave, and so it causes the water to basically bubble and boil. Okay, well, when we use that definition, there's another way that we could get the water to boil. What if we don't change the temperature? It's still at room temperature. You didn't see any heat underneath my beaker. There was no flame or anything there because there was no heat. That beaker of water was at 20 degrees Celsius. Well, it still is going to exert that 0.4 pounds per square inch, but now there's no air pressure pushing back against it. And so this is more than equal, the vapor pressure is more than equal for that water at 20 degrees Celsius compared to the atmospheric pressure, and so the water boils. It's literally boiling at room temperature. So in summary, normally the boiling point occurs when vapor pressure equals atmospheric pressure, and normally we heat it up to 100 degrees Celsius to get that vapor pressure equal to the atmospheric pressure. But in this case, we changed it. Instead of changing that vapor pressure of the water by heating it up to 100, we left it at 20 degrees Celsius, and the pressure left behind there inside the vacuum chamber is effectively zero for the air, so the water boils. I hope you enjoyed that demonstration of water boiling at room temperature.